And Professor Basu will be speaking about development of direct
cross-section of a fuel cell. So you have a porous anode structure infiltrated with copper or copper ceria or copper cobalt, copper iron kind of catalyst. This is your dense electrolyte, which is YZ, Testabilis zirconia, ganglion of ceria, and you have a cathode material with the LSM. Okay, you can see with hydrogen we have got 350 milliwatt per centimeter square. When we use butane here, C4H10, we got very good results, about 250 milliwatt per centimeter square, but different ratios in copper or iron. There was some deposition of carbon taking place. The main problem is the coking and carbon depositions. And then we tested about 50 hours. There was little degradation here, about 20 hours, but up to 50 hours there is no degradation, and we believe that it will maintain, and we did up to 200 hours and it did maintain the voltage. Okay, and then we did the same thing with methane with a copper iron ceria YSZ anode, and we checked with hydrogen as well, and as well as methane. You can see with hydrogen methane there is actually improvement in the results with methane because of the coking, and because of the coking there is a connection and electron conductivity. That's why the good results, and we get 250 milliwatt per centimeter square. This is a cross section, and after the cell operation, and there is no degradation. And you can see, normally if nickel is used, there is a degradation cracking. There is no cracking one can see on the cell, and there is no coke formation, because when we did TGA, a thermogravimetric analysis, and we see there is not much weight loss, and that means there is no coking or carbon deposition, which otherwise take place if you use methane, propane, butane as a fuel and you just burn it. There will be coking, and a black color carbon will deposit and will kill the cell. But here we show that it doesn't take place. Next, the last topic I want to talk about is glucose fuel cell. You have a lot of interest in biotechnology in this forum or in this conference. Okay, this is kind of micro fuel cell, micro glucose fuel cell we are working on. The idea is for body implant. So you have a pacemaker or you have a prosthetic finger, leg. You require power to work on. We can use lithium-ion battery for that. But can we use a body fluid? We can put a fuel cell inside your body and use the body fluid as a fuel. And can this work and give you power? The power required for pacemaker in the microwatt range or picowatt range, very small amount to run a pacemaker. If you have a prosthetic, you have a finger, or you have a bionic eyes, you don't want to carry a big lithium-ion battery, but if you have a small fuel cell planted with the bionic eyes here, which takes the body fluid, possibly glucose which is there in body fluid, can it run a fuel cell and gives you power, because you have electronic MEMS in your eyes, which is your bionic eyes or ears or your broken finger. You put an artificial finger here and you require power, or maybe your limb. So normally they use lithium-ion battery, but in futuristic it has to be some body fluid which is to be used, okay, for simply to making it more effective. So we were working on a chip to make a micro fuel cell, which is in a micron level channel, on which we have coated with the anode and cathode catalyst, and we are using glucose as a fuel. Here of course we are showing methanol, but we start with the methanol to show that it works for methanol, and then we also worked on glucose to show that we can actually generate energy by using glucose, and body fluid does have a lot of glucose. And then if you have a sensor, simple sensor planted in your body, and sensor requires power. Okay, so that power can come from glucose that you have in your blood glucose or in body fluid, has a lot of glucose. Okay, so that is how we started. Here it is shown is the glucose water, we give you gluconic acid. Gluconic acid is a product, and it is not poisonous to your body. You do produce gluconic acid in your body, otherwise when it goes through a normal microwatt per centimeter square in 5 months, that's what state of the art 2006. We started working after that, and we have improved the power output simply from microwatt to milliwatt range right now, and we have been cited a lot for this because there is a lot of work on diamond glucose fuel cell which is on microbe based or enzyme based, but you don't want to put in your body microbial fuel cell or enzymatic fuel cell because of immunogenic problem. But you don't want to put any microbes in your body. You never know what that actually can do in your body. If you put simple metal, no problem. Okay, we do put a lot of metal in our body and with a biopolymer engaging it. So it's not going to create a problem because you have a lot of artificial lean, replacement of your femur bone or all kind of bones and all of these. Okay, so that is what we were working on. So this is your glucose fuel cell. This is a small fuel cell that we made in our lab, which is actually casing is big. Inside it is our 1 centimeter diameter and 1 millimeter thick, which is shown you schematically here, anode and cathode, and open to oxygen this side, and inside this is your, which is your fuel, which is restricted here as like a batch process, okay, which we made first, and then we actually try to develop different kind of anode catalysts which will actually oxidize glucose into product, okay. So we were working on platinum, palladium, bismuth, platinum gold, platinum bismuth. So we got good result on platinum gold, platinum bismuth, which is blue color showing you high current, and if you see the poisoning effect, which is not much, even we get to greater scans. So we did a lot of studies on how degradation takes place. Okay, then we could go, as I said, microwatt to milliwatt, which is about 1.4 milliwatt per centimeter square, which we reported sometime in 2010, 11, and so on and so forth. So that was quite a big improvement from microwatt range or picowatt range of power output that Staten has shown in Germany sometime about 2006 or 7. Then what we have developed our anode catalyst. And at that time, most of the people working on microbes. And no, if you want to put in the body, that you should not be using it, as I just told you why. Okay, there's a substantial improvement. And further, we have used a new kind of electrolyte that was based on alkaline electrolyte with alkaline exchange membrane electrolyte, and we could further improve to about 5 milliwatt per centimeter square, which is a big improvement, and we had a lot of publication and a lot of citation as well. And then that was a little bigger in size. I said millimeter diameter and 1 millimeter thickness. This is really in micron range. So your fuel and oxygen coming. You don't require any membrane that we have talked about because it will maintain a laminar flow, and you can find out a load and then you can get electrons. So that's what a Y-shaped channel of micron size, which will be 100 micron length and width. So about 100 micron depth and width, and length could be a little bit millimeter, so that there is no mixing of two flow here, because it will maintain a laminar flow because it's a micron size channel. So that is what we made here, a micron size channel. In fact, part of the work is done in India, in ISC Bangalore, and in Toyo University, Japan, in Nano Bio Center, where one of my students goes and work. Previously worked, and also the collaboration is going on, which we have a common friend, Professor Shakti Kumar. He knows him very well. I also know him very well. So there, actually, he's going and working. Partly comes back to IIT Delhi and works there. We also have facilities. So it's kind of, we wanted to, it's not that you do things on your own, alone in the lab. You collaborate, you make a big group, you learn from them, he learns from you. That's actually we want to do. Indians really do less and less. We always think that we are self-sufficient, we are very self-centered in many ways. We should not do that. Wherever it requires, we should put our hand forward and embrace them, learn from them, and also they will learn from you. Because you have two hands, you have 24 hours, you cannot do everything on your own, as simple as that. Simply it is also same for them. So we should have, in general, we should try to help neighbors, we should try to help others, and they will help you in return. It will always happen. So everywhere you go, people try to collaborate, people try to learn and exchange ideas and the equipment which you share. That's a thing that you, at a young age, you should know. If you do that, then only you can flourish. If you don't do it, then you are going bound to, there will be no development at all. Okay? So that's what developed here, the channel. Then the channels where we have a metal patterning on the channel which is working as an electrode, which clearly shown one side, one arm is the anode, another arm is the cathode, which I just showed you here. One arm will go with the fuel, another will go with the oxygen. Okay? And then we showed you how to make it. So first design was making layer by layer, but we had a problem of aligning two arms because we developed separately the anode side and cathode side, and we wanted to put one after the other. But it's very difficult to align them like this. So we had to make both of them together. So this gave us very less power, which is of 0.0005 milliwatt per centimeter square. I said that normal cell we got such good results. In the micro fuel cell for this design we did not get good results. Here we got about 1.4 microwatt per centimeter square, which I talked about, which is millimeter scale. This was a micro scale, but we got a very bad results. Then we change our design. So we now making them as a parallel, okay, not one on the top of the other, but this channel which is parallel, and put the metal pattern together. That means I have a metal pattern this side and that side. Of course there will be gap. They should not touch. Anode cannot touch. Then it will short circuit it. So you have to keep them separate. So this is the schematic figure, and we do use a photoresist, a photolithographic technique with positive photoresist and negative photoresist, and make channels, which I'm not going to details of it this paucity of time. So you have to you have to read the UV, then you make a photomask, and then you take it out, and then you get a channel, and you can block the channel with a glass slide. You can use silicon wafer, then SU 8 and put a glass slide, so you get a channel which I show you here. And then this is a Y-shaped channel. Actually this is not running the video. I was trying actually hard from the morning, so it's not running. There's a video which shows that there's a flow in both the sides. You can see that I've used two kind of fluid, one with a color, this other color, so it maintains the level here, the interface here. There's no mixing, so that means no mixing taking place. Anode light and cathode light going in two arms. We don't record any membrane. Okay, so that's what we have done, and then we have done some other colloidal behavior and formation of some color here, which we done with the bovine serum albumin, BSA and Bradford reagent, which color, which is well known, to see that it maintains the interface. Okay, then we do the metal patterning with the anode cathode. I talked about already. Okay, this we do metal patterning in just using positive photoresist. The negative photoresist was used to make channel, while positive photoresist was used to make the metal patterning on the channel, which we do it, and we get this channel, and of course now you have a real one, but you can see some spots. That means there's some thickness was not pure. So there's some breaking point here. That means no continuity. So electron will not flow. But this one is better, which is almost like spotless, having one or two spots, but there is no break in the continuity. So that is what we have, and that's what we made, and we are working on it. So this is what we have. There's one bubble gone in, but then these anode, and then it clearly maintains between anode and cathode interface, anode light and the cathode light. So we are working on this, and then it was we used platinum. Platinum is costly, so we were using some new metal catalyst, which is not metal but CNA, carbon nitride, which works as a similar to platinum. So we made that as a fiber, and we showed that in situ voltammetry FTIR that they're active towards glucose oxidation or oxygen reduction reaction in this case. And then we are putting them, so the final device would look like this. You have two material, one is your fuel, other is oxygen, which is like storage. Then they come through this Y-shaped channel into it, and they go back, and it will last for hours together because you are using any small amount of fuel and oxygen. And this is the channel you have, and this is the power you are taking away, right? So, and these are the different kind of cathode, anode, heating pad, connecting leads, micro pump that you have here. The micro pump are very small micro pump, piezo based, and they are 20 euro cost, very small cost, 20 euro you can get a micro pump. And then you can get a chip like this, which will be of 5 centimeter, 2.5 centimeter, 0.5 centimeter, the whole size. But this channel is about 50 to 100 micron cross, 50 cross 100. Length is about 6 millimeter, because we want to produce more current. And beyond 6 millimeter, probably there will be mixing. So that is how we have made this length. And then you tap your electrons from here. So that device can be put in MEMS or any other places where you want to implant it. Quite a small device compared to your lithium and battery, but we are trying to make it smaller and smaller. Okay. In a summary, we only talk about micro fuel cell here in a summary, but I did show you about solid oxide fuel cell and ethanol fuel cell, which is also direct hydrocarbon fuel cell in different ranges, temperature, and this is of course a miniature one, and we got about 1.425 milliwatt per centimeter square. We're working on microfluidic fuel cell, and of course I would like to acknowledge the funding from DIT, Department of Information Technology, DST Nano Mission, another nano research facility at IIT Delhi, IDFC program in IC Bangalore, Biyani Research Center to University in Japan. And all my all my financiers, that because I listed out in the acknowledgement, we have a lot of projects with RC UK, EPSRC, Japan, NATO Japan, and then New Indigo, Gale R&D, ONGC, and DST, and MNRE. We have got a lot of projects for a long time. Right now also we have, and because of that only all of this is possible. So thank you for your time and listening to me, and if you have any questions, I will happy to answer.
Thank you, Professor Basu, for elaborating your research and especially the glucose is fuel cell technology that I think have a tremendous advantage while we are planning to plant devices. So now we are open for few queries from the students. Yeah, I want to know how much you understand the lecture.
Yeah, that's important. You should.
Yeah, any basic
Focus.
questions if you have. At least I expect 1 or 2 hands.
You can ask any question. If you understand, don't understand, you have to be free and ask whatever you have in your mind.
Yes.
So you talked about micro pump in that study. So micro pump is self-energized.
So micro pump is to flow. You have a sink where you are storing your fuel and oxygen, and it has to flow through the channel. So for that you will really require its high pressure to be maintained, and it requires power as well. So power will come from the cell priming kind of thing. The power will come from the same fuel cell. It will take away very little power. Very little power. Very little power. So it will come from the cell, whatever generated to start with. But starting also because you have micro channel, it will also some capillary effect. The process will start. But micro pump will be faster to pass the fuel through the channel.
So it will use the power from that fuel cell.
Device itself to run the micro pump, it requires really very small power. All this micro piezo based power. Very small power.
Sir, you talked about solid oxide metal fuel cell. In your slide, you showed that natural gas can be used to produce electricity directly. So, if we can use any gas which can burn, like methane, to produce electricity in that.
Yes, that's what I said. So you can use any gas directly, methane, propane, butane. That's what we are working on. Normally, if you talk about hydrogen fuel cell, people would take this kind of fuel, which is a primary fuel like methane, which is kind of natural gas available in the nature, to be converted to hydrogen by reform and then use in the fuel cell. That is what the technology developed. Everybody is demonstrating, like all car companies, you know, the Honda, Hyundai, and others, Chrysler and BMW, everybody. But you are spending some energy to convert methane to all the natural gas or the propane, butane or crude naphtha to hydrogen. But if you can directly use it, then you gain lot. Okay. But the problem is coking. So that is what all the time we were trying to answer in that problem, that how can stop coking, and can I do internal reforming within the cell where it would go through directly oxidation reduction reaction. Instead of making hydrogen, that going through oxidation reaction, propane itself goes through oxidation reaction, methane itself goes through oxidation reaction. That is what is a very challenging task. It's not that many people are trying. People have tried, given up also, but as a researcher, you should try to do that, isn't it? What people are doing already done, there's no point doing it. You have to do something new. Because if I can do it, then it's beneficial, and if I really can do perfectly, then of course you will know my name anyway.
Thank you, sir.
Is there anyone?
Girls should answer. I want girls to, you are girls college, and I'm happy to see that. Because we in our country, all we know, you are in city, possibly you are privileged, but in the countryside, girls are not privileged. So we should encourage and should help. And you also being a girl should help them. Please.
Sir, I want to ask you talked about ethanol liquid. So I want to ask that liquid is kept in it, or we have to pour it tank to tank for getting power?
I'm not shown you a picture, but it was demonstrated about 1999 by Mitsubishi, and then there is a like Sony 10 years back, and before that there's some other company who makes laptop, who made laptop first. I was just not able to remember the name of the Japanese company who made the laptop first. Toshiba. Like it is the Toshiba first who demonstrated laptop with a cartridge and a fuel cell at 1999 in a Hydrogen Expo. So the cartridge, like if you've seen a cigarette lighter, there's a cartridge. So you can take the cartridge, you can put more fuel, or you can put a new cartridge. So their design was a fuel cell having a cartridge at the back, which is like you can see like a glass having fuel, and you have to take, when it's over, just take it out and put a new cartridge. So fuel, which is ethanol, which is not a dangerous liquid to carry. Methanol, I agree. Methanol is a poisonous, so it has to be really carried very carefully in a box. But ethanol, there is no problem at all. If you use ethanol as a fuel, and you can carry it, the cartridge has to be carried. Once it is over, you replace the cartridge. That's what you require. And the requirement of fuel is very, very small. Very small. So it will take many months to big cartridge to get over.
So we can say that we can pour it or fill it the container after time to time.
Yeah, with the economically, if it's commercialized, then the fuel cell and the cartridge will be available. You buy a mobile phone and battery together, or then battery is gone wrong, you just throw it away and you buy a new battery. Similarly here also, so it will be available with the fuel cell and the cartridge. So your cartridge is over, you go back, go to that, they will fill the cartridge and give it to you. Or you buy a new cartridge. So that's the model they're looking at. Of course that was big, but now people have come with a small, Motorola demonstrated again, not now, about 10 years back with a mobile phone. So that small fuel cell. And then Lilliputian, there's a company in US which is not selling in the market, solid oxide fuel cell with charger, which is small charger. So like you have now lithium ion battery charger, which everybody now buys and carries for traveling, for charging, if you don't get a charging port. So they have a small, Lilliputian name of the company, and that makes a small solid oxide fuel cell, which actually for charging purpose. Like this small.
Both ways, fuel cell.
We are, some company comes to us, like right now ONGC would like to develop, they are working with us to develop solid oxide fuel cell for their wellhead. They produce a lot of methane. So if they, in the offshore, they require a lot of power, and methane, solid oxide fuel cell can give their power. Power comes down for photovoltaic. In the monsoon season they have a problem. That's we are working with GAIL. We are working on some project, similar project for the methane. Okay, and GE, sometime back they came for the glucose, but then I did not materialize. I don't know what is the reason, but GE showed a lot of interest in the glucose fuel cell once upon a time. Okay, so that is how we are working, but that's what I would like to answer to you.
But I hope there is a good application for micro.
Yeah, Japan, there is a lot of activity. Yes. Yes.
One last question. Yeah.
So you have said that we can use it in our body. How it is used and how it works in our body?
No, that is envisaged right now. It's not that it's being only a group in France in CRRS. They also working on similar thing. So they actually showed that if they made a cell which is biocompatible, they put it inside an animal and it survived. Okay, that's what they have tested, but it is not commercialized. This is a far-fetched idea using body fluid and using fuel cell to all these prosthetic things that are Biyani trials and all this talking about. So I really, if I say something, you will say that is for granted. No, this is just a development state. Okay, a lot of things to be still done, because something to do with the body means a lot of testing, a lot of permissions they have to be taken. So you can, like right now you have a pacemaker and the lithium ion battery is being put somewhere here or here. Okay, you just made a small cavity and put the battery and your connections, the wire connections there. So similarly, it has to be tested where in which part of the body it can be implanted and what body fluid it can use, or maybe confined it to a certain place that it takes the body fluid and that is being used. So all these things have to be still to be done. But it's a far-fetched idea, but it's a futuristic idea which many of us are working on. Okay? And a group in France, of course, I talked about, made one and put in the animal just to show this is biocompatible. It can sustain in the body and body doesn't show any effect on it.
Thank you so much, sir. This was really an amazing speech. So first of all, before moving ahead, I would like to request Professor Manish Biyani sir to pay a floral welcome to our respected Professor VP Singh sir.